so rapidly just by plugging it into the power socket? The answer is through DC motors. DC or direct current motors convert electrical energy to kinetic energy by applying the laws of electromagnetism. In this video, we will be demonstrating the concept of DC motors through a simplified model of an electric fan. This is our model. But before explaining how we made it, let us bring you through the fundamental physics concepts of a DC motor. A DC motor converts electrical energy into mechanical energy in the form of rotation of the wire coil. When a current carrying wire is placed in a permanent magnetic field, the conductor will experience a force. Why is this force generated? A permanent magnet generates a magnetic field like this, with field lines pointing from the North Pole to the South Pole. Next, when electrical currents pass through a wire, an electromagnetic field is created around the wire, with field lines wrapping around the wire in circles. When a current carrying wire is placed in a permanent magnetic field, the electromagnetic field interacts with the permanent magnetic field as shown here. The force experienced by the conductor is perpendicular both to the magnetic field and direction of the current. This can be illustrated using Fleming's left-hand rule. As shown in the picture, if the index finger points to the direction of the magnetic field and the middle finger points to the direction of current flow, then the thumb points to the direction of the force. Now that we know the fundamental concepts of a DC motor,
let us begin examining the materials that we will require and utilize in the making of our project.
A wooden board for mounting and anchoring the setup, thin insulated copper coil, magnets, a 9-volt battery, metal strips, wires with crocodile clip ends, sandpaper, paper to serve as fan blades, and scotch tape.
Firstly, the iron wire is secured to the block of wood with tape, ensuring that the wires are 2 cm above the wooden block and are 5 cm apart in a horizontal fashion. Its purpose is to hold the elongated copper wire in place. Next, roll insulated copper wire around a round object, for instance, a stack of magnets, to form a coil, making a wire loop that is 4 cm in width. Next, proceed to loop the wire through the coil through both exits to ensure that it stays consistently in shape, holding the loop together and also providing ends to be attached. Scrape off the insulated coating of one side of the elongated wire that extends from the loop using a rough object. Repeat again for the other end of the wire. Ensure that the insulated layer is completely removed of above mentioned areas.
Here's a list of safety issues and precautions you should keep in mind. First, exercise caution when handling the drill. If possible, ask a lab technician for assistance. Secondly, do not touch the uninsulated wire when the circuit is closed to prevent burns, injuries, and electric shocks. Third, avoid water at all times when working with electricity. Never touch any electrical equipment or circuits with wet hands.
Attach the wire loop to the ends of the metal wire, using the elongated ends to stabilize it in place. Proceed to connect 2 sets of crocodile clip wires to a 9-volt battery and then attach the other ends to the 2 respective ends of the iron wire. Here you can see the clips being connected in the process.
This is our completed electric fan model. Now watch what happens when I add the magnet underneath the coil. Just a little nudge and there. So why does it work? Take a look at the setup at this instant. As mentioned earlier, the magnet generates a magnetic field and the magnetic field lines are shown here. When I pass a current through the wire, the current will enter the wire, do a few loops through the wire, and then come out on the other side. We can say that at the topmost part of the wire coil, or here, the current is traveling to the right. To prove that the permanent magnet is necessary for the rotor to rotate, let's see what happens when you take away the magnet. the rotation stops. Now, notice that if you reverse the magnet direction, the rotor coil will also rotate in the opposite direction. Can you see why? The magnetic field will be in the opposite direction, causing the direction of the force to be the opposite as well. Now, let me go back to explain the significance of this step in the construction. Remember the step where we scrape off the insulation from one side of the wire coil? So here's what happens when you don't do that step. Initially, as explained earlier, the forces generated cause the coil to rotate. After half a rotation, what was initially the bottommost section has now become the topmost section and vice versa. Now the current in the new topmost section is in the other direction, and the force experienced is now again in the other direction. As a result, the coil will rapidly stop and rotate in the other direction for half a rotation, then stop and rotate again in the original direction, then stop again and change direction again and again and again. This wouldn't make a good motor, right?
In real life, direct current motors can be used for a wide variety of purposes that can make our lives more convenient. DC motors are used in many electronic systems around us, ranging from small objects like disk drives to large machines like cranes. Without DC motors, important items in our lives, drills, fans, elevators, will no longer function, and we will face major problems looking for alternatives to this convenient technology. Essentially, all machines that require a rotating component need DC motors for them to work, and hence, DC motors are extremely crucial and important to our everyday lives.